everyone. I am Vineet Kumar Sinha from APS Engineering College, Ghaziabad. In this video lecture series, we are discussing the subject Materials Engineering, and in Unit 1, that is crystal structure, the topic that will be being discussed today is mechanical properties and motion. So when external forces acts on a body, it undergoes some deformation. Due to cohesion between the molecules, the body resists the deformation. So the internal cohesion between the molecules tends to resist the deformation. Resistance to deformation offered by the material is known as strength of it. The quantity and the quality of resistance deformation offered by the material is known as strength of material. Now, if we branch engineering mechanism into static and dynamic, then static would be the study of the external forces acting on the body while body is at rest or motion. Similarly, the dynamics is the branch study where we take the effect of external forces without considering the deformation of the object. Similarly, when we talk about the strength of material, or the branch where we discuss the strength of material, it deals with study of internal forces acting on the body and also with considering deformation of object in the external forces. So appropriate sizing is necessary for objects to safely withstand the imposed forces on them and at optimal. Sufficient sizing would be required in our day-to-day real practical world uses of the material, so that to safely withstand all the imposed forces which is to be acted on them and at optimal cost. Therefore, strength of material is branch of engineering science which deals with deformation, that is stiffness, objects, strength and stability of atoms. Coming on to stress, what is stress and what is strain? When we discuss the strength of material, stress and strain play very major important roles. So stress is internal resistance. It is the internal resistance of a body offered by the material per unit area. This is considered as stress. This stress is denoted by sigma, and we can write it as force per unit area of cross section, having the unit Newton for force and meter square for area. Also Pascal, which is a unit of force. So basically, if we consider a body where the F or the force here it is applied uniaxially and tensile loading is there, tensile force is applied. And area of cross section, since it is a regular body, area of cross section is A. Then when we apply this axial force, tangential, unidirectional tensile force F, then reaction force Fn is generated. The internal resistance of the body which tends to resist this. The resistance offered by the body is generated as Fn, and here we can say the sigma average, the stress average is generated here is equals to F upon A. Sigma equals to F applied force upon A, area of cross section. So per unit area, the internal force generated to resist that is called stress. For any real world application, the different types of loading on any body may be tensile. The tensile loading means the force would apply such that the body will tend to increase its length as shown here. So if L naught would be the original length of the body as shown by the dotted line or dotted figure, after application of load, there would be a certain elongation. So the dotted line having LO and area of cross section A naught was initially the body, and after application of force F, in tensile condition, in tensile loading, it has elongated to final length L. Similarly, for compressive loading, the figure denoted by dotted line is the original shape of the body where the force, compressive force is applied. So it is given by L naught, and force is applied such that it will cause compression in the body. And the area of cross section is A naught. So again, the final length would become L after compression, and L would be lesser than L naught in the case of compressive loading, and here L would be greater than L naught in case of tensile loading, because here elongation is taking place and here compression is taking place. Similarly, two other modes of loading are there. One is shear loading, where the force would be applicable tangentially to the surface of the surface of the body or the area of cross section. If area of cross section is considered as A naught, then the force would be tangential to this area of cross section, and the deviation would be observed in theta, in the value of angle deformed, and similarly torsion also the angle phi. So these are four types of loading. The nature of forces developed within the body to balance the effect of external forces is known as internal resistance, that we already discussed, and tensile stress sigma equals to F upon A naught. So when we apply tensile stress, we can see here on tensile loading, typically for mild steel or any object, there is a breaking like this. The cup and cone formation will form, and there will be a neck formation. We'll discuss it subsequently. This is the typical tensile loading and failure. When force is applied in such a way, due to this, the length of the body increases. This force is called tensile force. The length of the body increases, and stress developed by this force is known as tensile stress. So how do we know it's a tensile stress? The length of the body tends to increase, or elongation will take place, and this force will be called tensile force, and the stress developed will be tensile stress. Here also it is shown. Originally the figure, the shape of the body was like this, and then it elongates and then further elongation. Similarly, compressive stress, the force is applied in such a way, due to this length of the body decreases. This type of force is known as compressive force, and the stress which is developed by using compressive force is known as compressive stress. Here we can see compressive stress. When we apply compressive force, this brick will go down due to compression. This is the loading condition for compressive stress. Shear stress. Shear stress is defined as the component of stress tangential with a material cross section. Shear stress arises from the force vector component parallel to the cross section. So parallel to cross section, if the force is applied or tangential to the cross section, then this will be called shear stress. Here we can show in this, we can see this figure. This is break. The failure is due to shear stress, and it is denoted by tau equals to dF upon dA. This is the expression for shear stress. The various tests performed to measure the mechanical properties are tensile tests or tension tests, compression tests, and also shear and torsion tests. Here we will discuss this tension and compression tests. So one of the most common mechanical stress strain test is performed at tension. These tests are typically observed in a stress strain curve and is performed in tension. The uniaxial tensile loading test is very common in material science. As will be seen, the tension test can be used to determine several mechanical properties. Several mechanical properties can be measured from these tests of materials that are important in design. From design point of view, few mechanical properties are very important while we decide to design a certain product or design the specification of certain product. A specimen is deformed usually up to fracture. Here in this tensile tension test, the specimen is usually deformed up to fracture with a gradually increasing tensile load. The condition is gradually increasing tensile load till fracture. That is applied uniaxially in a single axis along the long axis of the specimen. On the long axis of the specimen under tensile conditions. Normally the cross section is circular. Normally the specimen of the cross section is circular, but rectangular specimens are also used. A typical specimen for tensile test is as shown in the figure. Here you can see there is a reduced section, the portion of reduced section having two 1/4 inches length, and the specimen is having the reduced cross section of 0.505 inches diameter. The 2 inches of gauge length that would be applicable for calculations, having 3/8 inches radius and 3/4 inches diameter of the overall where we held that specimen into the machine. The universal testing machine where this test will be performed is shown here. It's having load cell where we can increase or decrease the load, and the specimen is being fixed here, and this is the moving crosshead which moves and the elongation of the material takes place, and an extensometer is fixed in at the uh, specimen at the place where it is where it measures the extension of the specimen. So stress sigma would be equals to F on A naught, and strain epsilon T equals to L minus L naught by L naught is the standard equation for tensile loading condition, because L, the final L, would be larger than initial length as elongation is taking place in tensile conditions. So epsilon T or strain equals to L minus L naught upon initial length L. Similarly, for compression test, a compression test is conducted in a manner similar to the tensile test, except that the force is uncompressive and the specimen contracts along the direction of the stress. So both are similar, just the direction of the force, applied force, is reversed. Other parameters are same. Now, typical stress strain diagram. Let's evaluate the stress strain diagram which we which we receive from a typical tensile uniaxial tensile loading test. So, a stress strain diagram for mild steel. Let's assess this first. So, if we plot a curve where y-axis would be stress and x-axis would be strain, where we have already seen stress equals to sigma equals to F applied force upon area of initial cross section O, original cross section, and strain sigma T epsilon T equals to L final length minus initial length upon initial length. So these are the condition, and these are plotted against x and y axis, stress and strain. Then a typical curve, stress strain curve for a mild steel specimen under tensile loading condition is being shown here. Here, as we increase the stress here, this direction, as we increase the stress, there would be some strain observed on the specimen, and the curve is linear up to certain point P. Then it would not be linear, and at certain point E, this is called a elastic point. We'll discuss one by one, and then it will go to upper yield point, then lower yield point, then maximum point S, ultimate tensile stress, and then the breaking stress P. So this is the elastic limit, the elastic portion. This is the region, this is the uniform plastic elongation region, and this is the necking region. This is the typical stress strain curve. Let's assess one by one. So what we saw in the last slide is a stress strain curve. So first we'll focus our attention on this region, this O to P region, O to P region, which is linear in nature, which is linear in nature. So elastic behavior and whose slope is equals to elastic modulus. Elastic behavior of material is represented by straight line. Stress is proportional to strain known as Hooke's law. During this part, stress is directly proportional to strain. Hence, the stress strain curve is a straight line. And this is called, this is the Hooke's law, where stress is directly proportional to strain or stress equals to E strain, where E is a constant called elastic modulus of elasticity. Hooke's law is followed up to point P is known as limit of proportionality. So the P is the point where this is unidirectional, this is a straight line, and this is the limit of proportionality. Young's modulus, the degree to which a structure deforms or strains, depends on the magnitude of an imposed stress. For most metals that are stressed in tension and at relatively low levels, as shown in the last figure, stress is proportional to strain, results in a linear relationship. Stress proportional to strain or equals to E strain. This is Hooke's law, and the constant of proportionality E in gigapascal is the modulus of elasticity or Young's modulus of elasticity. Now coming on to the next part, that is P to E. This region, this is P to E. P till P it was linear, straight line, having the P was the limit of proportionality. Now from P to A, after point P, curve no longer would be linear. So this P to E region, though it is seen like straight line, but it's not exactly the straight line. Point E is known as elastic limit. There is a point called E which is called elastic limit. That is, if load is removed upon reaching elastic limit, specimen will return to its original shape. So till point E, if we remove the load, what we are gradually increasing the load. If we remove the load, again the stress would become zero and the strain would become zero. Again, the material would be like this only. The specimen will return to its original shape. No change of shape would be observed. After point E, this elastic limit, after point E, there would be a plastic region starting. Starting with the plastic region, if load is removed beyond elastic limit, specimen will get permanent deformation. So from E to this YU yield point, the plastic deformation actually starts. And there would be no returning back while remove the load. There would be no returning to the original position, original shape of the specimen. Now, what is YU and YL? What is this YU and YL? Now, let's see this. A point where the stress causes sudden deformation without any increase in the force is called yield limit or point. So, when we increase the gradually increasing the load, there would be a point at YU, Y upper, where a sudden deformation will occur without any increase in the force. Now, having the similar force, there would be a sudden increase in the causing sudden deformation. So the yield point is the point on a stress strain curve that indicates the limit of elastic behavior and beginning the plastic behavior. So hard steels and non-ferrous metals do not have defined yield point. Therefore, a stress corresponding to a definite deformation, that is 0.2%, is commonly used instead of yield limit. Instead of mild steel, where it is shown YU is the critical, is the clear point, yield point upper and yield point lower, where we can assess that this is the strain point or this is the stress where yield point can be easily obtained. But for few materials other than mild steel, the curve will be like this and there is a gradual bending and there would be not a sudden increase or sudden yield point can be assessed. So in this case, the convention is for hard steels and non-ferrous metals, we have to define yield point corresponding to a definite deformation 0.2% used for yield limit. So as soon as this 0.2%, we take the strain as 0.2%, means 0.002 strain we take, and we draw a line parallel to the slope of elastic limit or proportional limit point, and wherever it cuts the stress strain curve, that would cause the yield point, and corresponding to that yield point, the stress obtained is called yield stress, sigma y, for those materials, the hard steels and other non-ferrous metals. To determine the yield point, a line parallel to initial stress strain curve is being drawn from 0.002 strain, and the intersection point gives the yield point. Now, with further increase in deformation, strength of the material tends to increase. The strength of material increases. This phenomenon is known as strain hardening. The strain hardening we learned previously also while we were discussing the edge dislocation or the plastic deformation. Dislocation movement, the restriction of dislocation movement happens, and therefore this strain hardening effect during plastic deformation increases the strength of the material, and amount of stress required to further deform the material increases and reaches to point E. So after start of the plastic deformation, the stress required to deform plastically keeps on increasing till this limit is achieved. So this sigma S or sigma UT and ultimate tensile stress UTS is being found out from here. So point E is known as ultimate tensile strength. Point E or point S, here it is shown S, so we can write S. After point S, necking in the specimen occurs, that is reduction in cross-section area of material, and finally fail at point B. After this curve, this S, the necking starts, the formation of necking begins, the neck area starts to form, and after a point, after certain time, after a certain period, at a certain stress, the material gets failed, the failure of material occurs, and it is a typical cup and cone type failure happens, where a formation of one portion is forms like a cup and one portion forms like a cone. That is called a cup and cone failure. Now coming on to strain, after applying load on body, the body gets deformed. This deformation is measured in terms of a dimensionless quantity, which is known as strain. So the deformation is measured in terms of strain. This is of three types. While tensile loading, the tensile strain will happen, where tensile strength can be obtained from L minus L naught upon L naught, as we discussed earlier, for a tensile loading conditions like this. For compressive strain or compressive loading conditions, epsilon T equals to, or epsilon C is equals to L naught minus L upon L naught. Similarly, the third term is shear strain. Here, the strain is not in terms of value, it is in terms of angle. So, epsilon S, shear strain equals to tan theta. If theta is the angle produced by as the effect of applied force, which is acting tangentially or parallel to the area of cross section, then tan theta equals to x upon L. X is the deviation, and L is the initial cross-section area. So x upon L is tan theta, and this is the value of shear strain. Can be derived from this equation. When a body is loaded axially, it deforms longitudinally or lengthwise, as well as transversely or crosswise also. And the following strain are developed: longitudinal and lateral. So if a body is loaded uniaxially under tensile condition or uh, along the long axis longitudinally, it also gets deformed transversely or crosswise also. Those are called lateral strains. So two types of strains are there: longitudinal and lateral. Longitudinal strain, the ratio of axial deformation to the original length of the body is known as longitudinal or linear strain. Axial deformation along the axis where the force is being applied to the original length, which is we know as general strain, is linear strain or longitudinal strain. This is given. This can be obtained by delta L upon L, where delta L is the change in length and original length is L. This is the same as L naught minus L or L minus L naught upon L for a tensile loading condition upon L naught. Now Poisson's ratio. So while we're discussing longitudinal and tensile and lateral strain or stresses, when a tensile stress is imposed on virtually all materials, an elastic elongation and accompanying strain epsilon z result in the direction of the applied stress, that is taken to be the z direction. Suppose in the z direction, the body is under loading condition, applied force is applied in at z axis. So sigma z is the main elongation, main strain, with the body gets deformed in this direction majorly. But as a result of this elongation, there will be constrictions in the lateral. There will be constrictions in the lateral x and y directions perpendicular to the applied stress. So perpendicular to the applied stress means other two y and x axis, it will move like this, and also it will move like this. There will be deformation again in the x and y axis also for a z direction, z axis loading condition. So overall, the compressive strains epsilon x and epsilon y may be determined if the applied stress is uniaxial only in the z direction. If the applied stress is only in the z direction and the material is isotropic, then epsilon x is equals to epsilon y, and it is opposite to the what is having in the z direction. Means if it is elongating in the z direction, then the x and y axis would be constricting and vice versa. A parameter termed Poisson's ratio mu is defined for this behavior as the ratio of the lateral and axial strains. So the ratio would be minus epsilon x upon epsilon z equals to minus epsilon y upon epsilon z. So sigma epsilon x is equals to basically epsilon y, and it can be found out from this relation. Now coming on to few properties of the material which is very important from design point of view. The first one is ductility. What is ductility? It is another important mechanical property. It is a measure of the degree of plastic deformation that has been sustained at fracture. So what is applicable, what is admissible till fracture, the degree of plastic deformation that may occur on that material is called its ductility. A material that experiences very little or no plastic deformation upon fracture is termed brittle, or vice versa, a brittle material gets fractured without having plastic deformation. So here we can see from the graph, if a stress and a strain curve is plotted for both brittle material, this is for brittle material, this red curve, and for ductile material, this blue curve. So till proportional limit and after that till elastic limit, the material, while increasing the stress, the material will not get the plastic deformation and it will break here only. This is the point of rupture or point of failure. So the total curve of stress strain curve without before failure would end here. It's like this only. So brittle material would not go for plastic deformation. So it is not ductile, it is brittle. And for ductile material, after the proportional limit, there will be an elastic limit, and after that, it will go on to a long way for plastic deformation, where the where the strength would get increased by strain hardening and subsequent failure at, at a very large strain. So it can be stretched to very large strain values. So ductility may be expressed quantitatively as either percent elongation, how much percent elongation before fracture, or percent reduction in area of the cross section of the material by necking. The percent elongation is the percent of plastic strain at fracture, and it can be obtained from the relation percent elongation equals to length final minus length original upon length original, that is strain, into 100. So percent elongation, yeah, percent strain is the percentage of plastic strain at fracture, and that gives the ductility. We can measure ductility in terms of percent elongation, where LF is the fracture length and L0 is the original gauge length as above. Brittle materials are approximately considered to be those having a fracture strain of less than about 5%. So the fracture strain would be, if it is less than 0.5%, means this is less than 0.5%, then it is called brittle material. If it gets fractured over here and it is greater than 0.5%, then it will be called brittle, called ductile. Now there's another property which is very important from design point of view, that is resilience of a part, the resilience of a material. Resilience is the capacity of a material to absorb energy when it is deformed elastically. How much energy it absorbs when deformed elastically till elastic region, and then upon unloading to have this energy recovered. So the material will be loaded up till elastic limit only, not beyond elastic limit, means no plastic deformation would happen. Only elastic deformation would be obtained, and upon unloading, the total the material will come into its original shape, and all of the energy which is being absorbed will be recovered. The associated property is the modulus of resilience, denoted by UR, which is the strain energy per unit volume, required to stress the material from an unloaded state up to the point of yielding. So since this is the area under curve till the yield point, and until up to the point of yielding, so this is called modulus of resilience. And if we calculate this UR as half into base into altitude, if it is considered as a triangle, if this is considered a straight line, then this would be the hypotenuse, this is the perpendicular, and this is the base. So UR would be given by half into base into altitude, half into stress Y, sigma yield, and strain yield, equals to half sigma Y upon E, because yield strain can be referred as yield stress upon elastic modulus of elasticity, or Young's modulus. So the relation becomes sigma square Y upon 2E. So U R, the modulus of resilience, is can be obtained from this relation is equals to square times the yield stress upon 2 times the elastic modulus or modulus of elasticity is the term modulus of resilience. Similarly, there is a property called toughness. It is also very important from design point of view. Toughness is a mechanical term that is used in several contexts. It is a measure of the ability of a material to absorb energy up to fracture. So it is similar to this modulus of resilience, but modulus of resilience is still up to yield point, and modulus of rupture or modulus of toughness is still up to fracture point or rupture point. So the area under curve of any ductile material or any material till the point of failure after whole elastic and plastic deformation is called modulus of toughness, or how tough the material is. So ductility and toughness goes along, means highly ductile material can be highly tough. Now when we are discussing the stress strain curve, we need to mention the true stress and strain analysis. Means the stress necessary to continue deformation past the maximum point M seems to indicate that the metal is becoming weaker. Since in our typical stress strain curve, what we have seen that after this point, maximum point where the stress is maximum, there will be further strain happening, but the stress associated is less. So it is suggesting that the material is getting weaker. So even if smaller stress is applied, the material is getting fail after some time or after necking. But in original condition, it is not so. How? This is not at all the case. As a matter of fact, it is increasing in strength. The strength of the material gets increasing due to strain hardening. However, the cross-sectional area is decreasing rapidly. Now here since necking starts or the beginning of necking happens, so the area of cross-section is decreasing rapidly within the neck region before deformation is occurring. This results in the reduction in the load bearing capacity of the specimen as stress is equals to force applied per unit area of cross section. So if the area of cross section is getting reduced, so what the force is applied, less force would be applied to break the specimen. And say if stress is calculated with original area of cross section, then it will be like the stress is decreasing. But actually it is not so. Actually the stress required to break the specimen goes on increasing. The energy, so this is called the true stress and strain. The engineering stress calculation is on the basis of original cross-section area before any deformation and does not take into account the reduction in area at the neck. Sometimes it is more meaningful to use a true stress strain scheme. So true stress, that is denoted by sigma T, is defined as the load F, what is being applied, divided by the instantaneous cross-section area, FAI, over which deformation is occurring. So before the necking starts, it is equals to A naught, and after the necking begins, it is AI, instantaneous area of cross-section at any point of time. Similarly, it is more convenient to represent strain as true strain, epsilon T in place of epsilon, defined by epsilon T equals to log of Li upon Lo, where Li is the instantaneous length at that point of time and Lo is the original length. So now if no volume change occurs during deformation, if we assume that during deformation, volume is not getting changed, means either the stress or the area of cross section or length is getting changed, but volume remains constant, then we can have AI Li at any point of time if AI is the area area of cross section, instantaneous area of cross section, and Li is the length at that instantaneous instant, and A naught L naught is the initial area of cross section and length of the specimen. Then true and engineering stress and strain are related. It can be derived as sigma T, sigma true is equals to sigma 1 plus epsilon, and sigma epsilon T, epsilon true is equals to log 1 plus sigma. This can be deduced, but it is not required at this point of time. But by very conveniently, it can be derived from the, if we consider AI Li equals to A naught L naught, then we can easily take up this sigma T equals to sigma 1 plus epsilon relation, and sigma T is equal to log of 1 plus epsilon. So this is the true stress and strain as per the relation. Now, malleability is also a property of a material. It's a physical property of metals that defines their ability to be hammered, pressed, or rolled into thin sheets without breaking. It can be pressed, hammered, or rolled into thin sheets. Or how easily it can be done into thin sheets without breaking is called the malleability. In other words, it is the property of a metal to deform under compression and take on a new shape. So while we compress any material, and when we compression compressive forces would be applied, how well it behaves or how much it takes the compression and changes into new shape or hammered, pressed, or rolled into thin sheets is called the malleability. So malleability is the property of a metal that allows it to deform under compression, while ductility is the property of a metal that allows it to stretch without damage. Now, there is a term elastic recovery or elastic strain recovery. This is also important. Let us see. Upon release of the load during the course of a stress strain test, some fraction of the total deformation is recovered as elastic strain. And if we wish, if we desire, we can recover some elastic strain or some deformation as elastic strain while unloading after some time, some gradual, after a certain point of time. If we unload the material, the loading gets removed, there would be a recovery of strain that is called elastic strain. During the unloading cycle, the curve traces a near straight line. Suppose a stress strain curve is obtained like this, and if we go from 0, if we keep loading the material, tensile loading starts, then it will be a straight line till point P, limit of proportionality, then point E, elastic limit, and after beyond that, plastic region means there would be a plastic deformation from here to here. Now no more recovery. From this point, if we remove the load, again the body will move to this condition where no strain and stress is 0 and strain would be non-existing, and the material will come into original shape. After this E also, it would be not linear at this while, but still the material will come back to its original shape till the elastic point. But once it will reach elastic point and beyond, the plastic deformation gets started, and while if you unload after this point, it will not reach to this condition, but subsequently if you remove the load, this will again come back parallel to as per the slope of this elastic condition, but it will stay here, means there would be a permanent strain applicable for that load. Even if we remove the stress completely, unload the material, there would be a certain plastic deformation denoted by this strain, whatever is occurred. But if we, so since it is not, since it follows the slope of the curve of the plastic strain or elastic strain, so this elastic recovery, this recovery from this point, at this stress point, the strain would be this. The strain was this. And after unloading, the strain is becomes less than this. So this would the elastic strain which is being recovered which is would be same as this strain. So this is elastic strain recovery and it's called elastic recovery in general. So during the unloading cycle, the curve traces a near straight line path from the point of unloading and its slope is virtually identical to the modulus of elasticity or parallel to the initial elastic portion of the curve. If the load is reapplied, the curve will traverse essentially the same linear portion in the direction opposite to unloading, and yielding will again occur at the unloading stress level where the unloading began. So when we again load the material, it will follow the same path and it will now the yield point will be like this, and then further plastic deformation will get started. So this was all about elastic recovery, and this is all for this video lecture, and we'll discuss more topics in the coming video, further videos. Thank you.